Before our third class meeting, please watch this video and then skim through chapter 3 of Mazur's textbook. Mostly you're going to focus on the concepts half. In the equations half, don't let yourself get bogged down in the large number of equations you'll see there. Any equation that's actually important you'll see in this video. So I think the book is more important for the concepts. This video will show you all the equations that you're going to need. This is another example where I think you can get through the chapter more efficiently if you watch the video first, but you're free to do it in the other order if you wish.
Let's start today's lecture with a quick hello from Professor Farley, who's been teaching architectural structures here at Penn for a couple of decades. Then we'll come back and talk about Mazur's chapter 3, which is about acceleration.
Hello, welcome to Architectural Physics. I'd like to spend a few minutes talking about the importance that physics plays in the world of architecture. So to get started, let's go through a few images. So I'm Richard Farley, and I'm an architect, and I also teach over at the Weizmann School. And the course I teach is the first year, the MArch program, graduate program in structures, how to hold things up. And certainly the importance of understanding Newton and Hooke and all of the laws of physics play a tremendous role in terms of what I teach, as well as other technical courses in the program. Maybe the best way to start is to go back and look at the Romans and to contemplate a building that is my favorite building in the world, the Pantheon, and understand how forces are moving through that and understanding the physics that's at work here to be able to create this tremendous, amazing building. The building spans with a gigantic dome, a length of 144 feet, just tremendous length. And the key to it is, the key amazing thing about it is that there is no reinforcing, no steel in it at all. It is pure concrete that's up above your head, holding everything at bay in terms of those forces wanting to descend down to the ground in the gravity field that we're in. And up at the top, as you've probably known if you've gone there, there's a tremendous oculus hole that reaches up and into the sky so you can see beyond. And if you notice up at the top of the dome, everything is solid, which means that's where there's a tremendous amount of compression that's pushing in. And that concrete is working as best it can to make sure that that compression up at the top is held at bay. Obviously, with the weight of that ball trying to push down at the base of the dome, there's a tremendous amount of tension trying to pull it out. And the Romans were very clever at how they dealt with that. So if you look at the building in section, you'll notice that as you come down the dome, they've created a thickening more and more so as you get down towards the base of the dome. In effect, pre-stressing, pushing in on the bottom of the dome with weight to counteract any tension that's occurring there. Extremely clever. The span, as I said, is of a tremendous length, and it is one that we even think very much about how we would do today. So again, the world of physics as it plays of bringing all that weight down into the drum of the Pantheon is key to understanding how the architecture is created and performs. So an image of a model of the outside of the building shows that these rings are placed at the outside of the building, all pressing down and in, keeping everything stable. Right? If we leap forward into the Gothic, we look at the Notre Dame Cathedral, and as you know, it's unfortunately undergone a tremendous fire and that is in the process of being rebuilt in its exact form. I kind of neglected the tower because the tower comes from the 1800s, but I really want to concentrate down here on the stonework and to be able to create a laciness, to be able to get as much natural light into this tremendous vaulted space. The Gothics knew enough about structure to be able to take that thrust. The thrust is the pushing out of the base of the roof and take it down into these flying buttresses over to the side. So very much like a hook and ladder, fire truck goes up to be able to access a higher floor. At the base of the truck, they typically roll out these devices on the side and push down on the earth. Buttresses are the same way. They're out there helping stabilize and take care of all that lateral load that would be present from the action of wind up against the top of the roof, and certainly the weight of the vaults that are inside trying to push down. I have a quick view of a vault. This is not from Notre Dame. This is from Saint-Germain, which is even older, which shows a whole series of vaults that are pushing out on the side, that weight trying to come down, having to be counteracted by the bulk of the outside walls, the action of the outside walls. If we go forward now, finally get to the world of Hooke and Newton, realize everything moved that before that has not had the benefit of Newton telling us about force equals mass times acceleration, that every action is an equal and opposite reaction, and all objects remain at rest unless acted upon by an unbalanced outside force, and anything in motion remains in motion unless acted upon by an outside force. Rennes, St. Paul's Cathedral, is right about the same time that Newton is writing his famous book that gives us the laws of physics. And you can see that the intelligence went into the building, making the building the dome a little bit more parabolic, which is more responsive to the loads that are on it. If you have a chance to go there, take a look, and you can go up whole series of stairs and go up into the dome and understand that it's actually a double dome. There's an interior dome that's a pure semicircle, doesn't have any of the wind loads on it, a little bit easier to form that. But as you go up into this tremendous space that's formed between the interior dome and the outside dome, you'll see a tremendous number of wood trusses, essentially, that are reaching up, that are taking the heavy weight of the cupola up at the top of it to be able to channel it down into these sidewalls and then down, and finally finding their way into the foundation. Again, the physics of this is tremendous in terms of creating the tremendous sensation that St. Paul's Cathedral. Hopefully in a few months, Bill will invite me back to talk about this Millennium Bridge that's over here, which celebrated the turn of the century. And it has a kind of an interesting past on it, that it was open for one day. It just was too active and swaying back and forth. The wave action of it got to be unsafe, and the bridge was actually closed for some period of time to be able to make adjustments to it. But we'll talk about that later on in the semester. If I go and I look at another genius that I have tremendous amount of admiration for, Eiffel. And at this point in the evolution of construction and structures, we have analytical tools that are telling us how winds and loads are going to, waves are going to act as loads through a structure and be carried down into the foundation. And the cleverness of this building, the efficiency of this building was just a tremendous point in time that advanced us into an age of modern building, my opinion. So we take a look as we go into the 19th century of all of the shift of the world, energy and focus in terms of innovative structure moving over into the United States. And the bridges that we built and the high-rise buildings we built at that time challenged span horizontally, and it also challenged height and set a new standard for how we were going to proceed in the world of architecture. So we move over to Paris and we take one last look at what's happening right now in terms of architecture. And this is a building that was done about 5 years ago by Frank Gehry, well-known American architect. And it is a museum. It's a Louis Vuitton museum. It's well worth going and take a look at just for the spectacle of how the building is put together. And when you compare this to the Pantheon that we looked at earlier on, you're kind of scratching your head and you're wondering what, how, yeah. And part of that delight of this architecture is the fascination of how it's all held together and put there. It's not so easy to be able to look at this building and understand how loads are being channeled and taken down to the ground. Certainly compare the two, and it's kind of an obvious contrast. Right? And then let's all go up to New York, and you can go over to Hudson Yards and you can see this amazing sculpture structure that's up there that's called the Vessel. And again, take a look at how this must be stabilizing itself. There are no columns in here. So somehow that load is all being channeled down through the frame of this structure and be able to brought down into the foundations, and all done quite safely and properly with stability at hand. So exciting things by understanding the basic principles of physics. Now, I understand that a number of folks in the class are not in the architecture major, and I think it's really important to underscore the fact that the ability to understand the basics of physics and to be able to ask intelligent questions, whether you're in land development, whether you're in acquisitions of companies, to be able to look and understand things in a way where you can ask questions in an intelligent manner and receive information to be able to make you well informed to make proper judgments and proper decisions as you go forward. So I think you're all in good stead with Bill, and I will see you in person as the next few weeks go along. And I'll leave you with this one last image behind me, which is poking through the clouds. And this is the Kingdom Tower in Saudi Arabia. That's 1 kilometer tall. So gigantic, 0.6 of a mile tall. And curiously enough, the structure in here, if I had to create its pedigree, to go back and tell you which of the buildings we looked at today is most like it in terms of structure, it would be the Pantheon, of carrying through walls. And it's 3 major intersecting walls that are coming down, going this height. They carry that load straight down into the ground and are pinpricks into the coral that's underneath Jeddah in Saudi Arabia. So I look forward to meeting any of you. Any questions, you can certainly get back in touch with me. I think I put my email up on that first slide. If not, it's rfarley@design.upenn.edu. And look forward to seeing you in person. Take care.
So let's start by defining acceleration. So last week, we learned that velocity was the rate of change of position. So we're going to take one more step this time and say that acceleration is the rate of change of velocity. And remember, we are dealing only with x components for the first 9 chapters of the textbook. So in particular, last week we saw the x component of velocity is the rate of change of the x component of position with respect to time. So v sub x is dx by dt. So the new addition this time is that the x component of acceleration is the rate of change with respect to time of the x component of velocity. Let me make sure this looks like a subscript. This is v sub x. So a sub x is d by dt of v sub x. We also learned last time to identify v sub x, the x component of velocity, as the slope on a graph of position x versus time t. Now, moving at constant velocity is not all that interesting, so we want to be able to talk about changes in velocity. And if the velocity of an object changes, then we say that object accelerates. Well, an object accelerates if its velocity changes, and in particular, acceleration is the rate of change of an object's velocity. So again, the rate of change of velocity with respect to time is called acceleration, and the x component of acceleration is the time rate of change of the x component of velocity. While it does turn out that acceleration can also vary with time, it turns out there are many situations for which constant acceleration, in other words, a sub x is a constant, turns out to be a good and a useful description of the motion. Soon we'll see what a little bit of math lets us conclude if we start with the assumption that a sub x is constant. So if we start out with the statement that the acceleration in the x direction is a constant, we'll just see what calculus lets us derive from that assumption. So let's start by looking at a graph of position x on the vertical axis versus time t on the horizontal axis. So this graph wants us to focus our attention at time t2, which is over here. So I guess we want to focus on what's happening somewhere around this point. And at time t2, the question wants us to ask, is the object not moving? Is the object moving at constant speed? Is the object speeding up? Is the object slowing down? So let's go through one by one and try to either confirm it or rule it out. Is it not moving? What do you think? I think it is moving because if it were not moving, then x would be unchanging as a function of t. So because x is changing as t increases, I think it is moving. Is it moving at constant speed? Well, if we're moving at constant velocity, then the slope of the x versus t curve would be constant. Speed is actually the absolute value of the x component of velocity for one-dimensional motion. But still, I think the magnitude of the slope of this curve is changing. So it is not moving at constant speed because the magnitude of the slope of this orange curve is changing with time. Is it slowing down? Let's consider d first. Is it slowing down? So as time increases, it seems as if the magnitude of the slope is getting bigger and bigger. So I actually think it is speeding up. That's C, Charlie. That's because speed is the absolute value of the x component of velocity in one dimension. And we can see that the slope is becoming more and more and more negative as time goes on. The speed is indeed increasing. So I think I like C, Charlie. It's speeding up. Okay, at the same time, t2, is the x component of velocity 0? Is it not changing? Is it increasing? Is it decreasing? If we look at the x component of velocity, the x component of velocity is just the slope of this x versus t curve. So we have x plotted as a function of time t position, x on the vertical axis, time t on the horizontal axis. At this time t2, this question is really saying, is dx by dt 0? No, it's not 0 because there's a non-zero slope. Is dx by dt not changing? Well, I think it is changing because I think dx by dt is negative here, it's more negative here, it's more negative here, it's more negative here, it's more negative here. So I think it is changing. And I think, as a matter of fact, dx by dt is decreasing. I think I like d, delta. So the magnitude of dx by dt, well, by the way, right, speed, right, was the magnitude of dx by dt. So in the previous slide, we concluded that the magnitude of dx by dt was increasing, but dx by dt itself is decreasing because it's a negative slope, and that negative slope is becoming more and more and more negative over time. So the object is speeding up, but its x component of velocity is negative and is becoming more negative. So I would say that v sub x, the x component of velocity, is decreasing at time 2 here. I guess we've given away a little bit of this answer. Is the x component of acceleration in these two graphs, here's graph A and here's graph B, is it positive in A, negative in B, negative in A, positive in B, blah, 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 blah. Okay, let's figure out the sign. In other words, let's figure out the sign of the acceleration in each graph. Well, I guess it's for the whole graph. It doesn't say at time t2. So if we look at the slope at t1, it is a negative slope, and at t2 it's a more negative slope. So this slope is negative, so the velocity is negative, and the velocity here is becoming more negative. So this is v sub x is less than 0, and this is v sub x is even more negative than that. So you go from negative to even more negative. That's a negative change. So I think that the acceleration, the x component of acceleration, is negative in the first graph because we have small negative slope here, and we have an even more negative slope here. V sub x is negative, but of small magnitude, and now it's negative, but of bigger magnitude. So it got even more negative. So that's a negative change. To make something more negative, you have to subtract from it. Okay, then in this graph, I still see a negative slope here, but now the slope is becoming less negative. You see? So this is a negative slope, but this is a less negative slope. So the slope is negative, but it's becoming less negative. So to make something go from negative to less negative, you have to add something positive to it. So I think that the acceleration is negative in the first case, and the acceleration is positive in the second case. I would go for Bravo here. Acceleration, a sub x is negative in A, and a sub x is positive in B. This is tricky because you see v sub x here is negative, and here v sub x is more negative. So you have to subtract from it to make it more negative. Here v sub x is negative, and here v sub x is less negative. You have to add to it to make it less negative. Whoa. So one important situation where where constant acceleration gives a good description of the motion, is so-called free fall near Earth's surface. And remember, I'm going to say it one more time, that up through Chapter 9, we're only going to use one axis in any given problem, and we will always call that axis x, no matter what you learned in your previous physics course. For free fall problems, for now, up through Chapter 9, the x-axis will be vertical, pointing upward. So for free fall problems, we're going to have the x-axis pointing upward like that. Free fall is the motion of an object subject only to the influence of gravity, no other influence. Later we'll say no other force, but we don't know the word force yet. So subject only to the influence of gravity. That means it's not being pushed or held by your hand or by the ground. And it also means that air resistance is going to be small enough to neglect. Close to Earth's surface, an object in free fall experiences a constant acceleration whose magnitude is 9.8 meters per second, which we also call 9.8 meters per second squared, and points in the downward direction. Now, to avoid saying 9.8 meters per second over and over again, we give this a name. Free fall near Earth's surface, we have a sub x is minus g, where little g is 9.8 meters per second squared. So because it's negative, the acceleration points in the downward direction, which I think makes sense. So again, if we define the x-axis to point upward, as we often will for free fall problems until we get to Chapter 10, then a sub x is minus 9.8 meters per second squared. You probably haven't seen checkpoint 3.7 yet, but let's go through it together right now anyway. Does the speed of a falling object increase or decrease? You should think about that for a minute. As an object falls, so if it's falling, does its speed increase or decrease? And if the positive x-axis points up, does v sub x increase or decrease as the object falls? And is the x component of the acceleration for a falling object positive or negative? You should probably pause for a minute to think about your answers to these questions. I suggest you might want to draw a graph of v sub x versus time for a falling object. Remember, we're going to define the x-axis to point upward. I'm going to draw my own graph. We said falling, here is time, and here is the x component of velocity. So if we say falling, I think that could mean, for instance, I just drop an object like that. So if I just drop an object like that, it starts out, when I first release it, its speed is 0, and then because we have a sub x is minus g, v sub x starts out at 0 and then becomes more and more and more negative over time. And this slope is minus g. So the slope is minus 9.8 meters per second. The vertical axis here is velocity. It's measured in units of meters per second, and it's plotted as a function of time. And its slope with respect to time is meters per second, because it's how many meters per second do I change per second. That's if I start something up like this and just drop it. There are actually other things I could do. I could toss something up in the air and let it come back down. And we'll see an easier to watch video of that in a minute. So if I do that, if I toss something up in the air and let it come back down, and when I first release it, it has a big upward velocity. So in that case, we'd start out with a positive value of v sub x, but you still have the same slope. There's a straight line, so here the same thing. Slope is minus g. The slope is minus 9.8 meters per second. Even though I'm not a good artist, this is a straight line. This is a straight line. Those two straight lines are parallel to each other. But in this case, we started out with an upward velocity, and then the velocity becomes less and less and less upward, and then it becomes more and more and more downward. But the slope doesn't change from the instant after I release it until the instant before it hits the ground. And here I just dropped something from up here. So it started out with 0 velocity, and then the velocity becomes negative and more and more and more and more negative. So that's the initial conditions changed that. If you're really talking about an object which is falling, see, now this is interesting. This is actually, I would want to go back to the question, the checkpoint, and ask what exactly is he asking? Because usually when you say something is in free fall, if something is in free fall, it actually could be going up, like after I threw it in the air. It could be in free fall that whole time. So if it's in free fall, but it's not falling, you see, it could be in free fall but going up. So if I throw it up, but it's in free fall, it actually slows down. See here, I started out with a big upward velocity, and you see it slowing down. For an instant here, it has 0 velocity, and now it's speeding up. But I'm going to take the question at face value. He says falling, and usually falling is a special case where you say it's falling downward. So in that case, I would say it probably starts out with 0 velocity, and the velocity gets more and more and more negative. I think the speed increases, and that's as long as it's falling downward. If it's falling downward, the speed increases. If it's in free fall because you just tossed it up in the air, then for that upward part of its journey, its speed decreases, actually. And now I'm embarrassed. I didn't go and look at the checkpoint more closely to see whether he's really saying it's falling downward or not. Okay, now the positive x-axis points up. Does v sub x increase or decrease? Now this is true no matter whether I started it by throwing it up or I started it by just dropping it. So in either case, v sub x decreases. So you see here, v sub x started out positive, but it's decreasing at a constant rate. Here, v sub x started out at 0, but it's decreasing at that same constant rate. So either way, v sub x decreases as a function of time, because the acceleration, which is the rate of change of v sub x, is negative 9.8 meters per second squared. Is the x component of the acceleration positive or negative? It's negative because the object is accelerating downward, and we've defined the x-axis to point upward. The x component of acceleration is negative. I think now, when you actually get to that checkpoint, you'll probably read it more closely than I did. Now let's take a little video break and do something that Galileo could only imagine doing. Let's see if different objects really do fall with the same same acceleration, a sub x equals minus little g, if we're able to remove the effects of air resistance. So we'll take a little break and watch a demonstration where we will see different things appear not to obey this rule that a sub x is little g, and then we'll see that if we get the air out of the way, we revive the statement that a sub x equals minus g. We introduced velocity as the rate of change of position with respect to time, and we introduced acceleration as the rate of change of velocity with respect to time. It will turn out that there are a pretty large number of scenarios that are usefully described by the assumption that acceleration is a constant. And one of those cases that will come up pretty often is an object in free fall near Earth's surface. We'll understand this in more detail when we study forces later, but free fall basically means that the only non-negligible influence on an object is the gravitational attraction between that object and Earth. If we take a basketball, I can drop it, and my approximation is that the basketball is in free fall. And what that means, free fall near Earth's surface, means that the object falls downward with an acceleration. The acceleration points toward the center of Earth, and the acceleration has a magnitude of lowercase g, 9.8 meters per second squared. Here, I'll drop this basketball from, I guess, a little less than 2 meters in the air. We'll see it bounce. Actually, you can see something interesting is going on from the fact that it doesn't bounce quite to its full height, but we'll talk about that next time. Okay, so our model is that this basketball is falling toward Earth with an acceleration, a downward acceleration, whose magnitude equals g, and that this is the same acceleration for all objects in free fall near Earth's surface. Now, you know that that's a little bit of an idealization because, for example, I can take a steel ball and a styrofoam ball, and I can drop them together. And I think intuitively you know that the steel ball will hit the ground before the styrofoam ball, but somehow that seems to contradict this idea that everything falls at the same downward acceleration of g, of 9.8 meters per second per second. Okay, let's just confirm our intuition. So first I'll do it from a height of about 2 meters, and we'll see if you can both see and hear how the two objects strike the ground. So let me do one at a time. Here is the styrofoam ball, and you can just barely hear it. And then here's a steel ball, which is much more obvious to your ear. Okay, and let me drop them together from this height of just under 2 meters. And we'll make that more obvious in just a moment. We'll go up to maybe 3 or 4 meters height. Often in physics problems, we try to describe things in terms that better fit the model that we're using. So if our model is that things near Earth's surface fall with a constant acceleration downward of g, then we'll talk about a steel ball dropped maybe just from 2 or 3 stories in the air. Whereas if instead we talked about a wiffle ball, or this styrofoam ball dropped from 2 or 3 stories in the air, then it seems that falling at a constant acceleration of g is not the full story. There's some other influence, and we'll argue in a moment that other influence is the effect of air resistance. And we don't really want to quantify air resistance in this course, so instead we'll focus on problems in which air resistance is not so important. Even for a steel ball, if we dropped a steel ball from the top of the Eiffel Tower, air resistance would become important. So we're going to say we're dropping things whose size and shape and mass is such that when they fall near Earth's surface, air drag is not too important. And we're also going to drop them from not too big an altitude so that they don't gain such a gigantic speed that air resistance then becomes important. If you compare these two objects, you can see that this one is more dense. So the more dense one will better approximate this model that everything falls at a constant acceleration of g, because air drag is relatively more important for a less dense object, given the two objects of the same size. And then it also turns out that air drag becomes more and more important at higher speed. So we're going to drop things from not too high so that they don't reach such an enormous speed by the time they hit the ground. So let's drop this from a little bit higher up. So now I think I'm going to drop this from maybe 3.5 meters in the air. You can both listen and watch as they hit the ground. I'll try to release them at the same time. Let me do that one more time. Okay, so we have styrofoam and steel, and you can both listen and watch as they hit the ground. Let's make the contrast even maybe a little bit more dramatic. So in this cylinder, we have a penny, a copper US 1-cent coin, a penny, and a feather. All right, so now the tube is oriented horizontally. So if I rotate it 90 degrees, then the two objects will fall toward Earth's center. I guess if the simple rule that acceleration downward is a constant g were true, you would see both objects travel the length of this tube in the same time interval. But, okay, you heard the penny fall. And then several seconds later, you saw the feather still traveling downward. Let's flip it over and try again. Yeah. The penny reaches the lower end and even bounces a little bit, and the feather is still making its way down. Okay, And I claim that the difference between the feather's descent and the penny's descent is that the feather is much more highly influenced by air drag than the penny is. The model that the only influence that matters is Earth's gravity is pretty good for the penny, but it's not good at all for the feather. There's a famous video, which we may paste in, of an astronaut dropping a feather and a hammer on the moon and seeing them descend together. We can't go to the moon for this video, but we actually can remove all of the air from this tube. Let's do that. We are going to use this vacuum pump to pump all of the air out of this tube, and then let's repeat this experiment and see what happens when the penny and the feather fall. Let's see if the approximation that the acceleration is downward g for all objects looks a little better if we get the air out of the way. It makes pretty cool noises. Okay, now I'm going to turn this little valve so that the tube is sealed. Now I can turn the pump off, I can disconnect the pump. Okay, so I claim that I have evacuated the air from this tube. So you still see the penny and the feather at the bottom. So let's see now what happens when we flip this upside down. Let's see if the penny and the feather now seem to travel at the same time. So in other words, let's see if this approximation that the acceleration is downward and has magnitude g seems a little better. Here we go. Oh, that's pretty good. Let's try it again. Let's try it again. Oh! Yeah, you can see the feather and the penny hitting the bottom at the same time. Wow. I think that's pretty cool. In the absence of air resistance, it really is true that all objects fall near Earth's surface with a downward acceleration of lowercase g, which is 9.8 meters per second, or 9.8 meters per second squared. But that observation is complicated by the presence of air resistance. So in order to make the model useful, sometimes we need to restrict our attention to relatively dense objects moving at not too great a speed. Or we can just get the air out of the way by using this pump. Now let me just, to show you that nothing nefarious is going on here, I will let the air back in. And sometimes the feather moves around in a crazy way as we let the air back in. Let's see what happens. Also, sometimes you get a little bit of condensation. Okay, so the air is back. Now let's see if we return to the previous situation where the feather takes a much longer time than the penny. Yeah. Good. Good. In the absence of air resistance, which we can minimize by restricting our attention to relatively dense objects which aren't moving too fast, like a steel ball dropped from maybe just a few stories in the air, all objects near Earth's surface fall at constant acceleration downward with magnitude lowercase g, 9.8 meters per second. But you do have to be careful to arrange things so that air resistance doesn't confuse you.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Let's work out some of the results that we can derive from the assumption that a sub x is constant, that acceleration in the x direction is a constant. Now, you do not need to know how to do these derivations. Not everybody has learned calculus, and even if you did at some point learn calculus, it might not have been an experience you enjoyed. That's perfectly okay. Some of you know calculus and like calculus, so if you like calculus, you can watch closely. If you don't like calculus, you can cover your ears, but just be aware of the fact that these results that we use for constant acceleration are simply this assumption that a sub x is a constant, and then we'll do a little bit of math. We know dv sub x by dt equals a sub x. That's just the definition. We can then, if we like calculus, we can integrate both sides. On the left-hand side, if we integrate dv sub x by dt, starting at t equals 0, and we go up to t equals t, so from 0 to t. On the left-hand side, we get v sub x of t minus v sub x initial. And on the right-hand side, so if you have a constant and you integrate a constant, you basically just multiply by t here. So that's a sub x times t. So what does that say? That says that v sub x at time t equals v sub x initial, which means at time 0, plus a sub x times t. So we integrated both sides, and that's what we got. Sometimes it's easier to do derivatives than integrals, so it might be worth just saying, let's go backwards here, so that if you don't like integrals but you think derivatives are okay, we'll see that it makes sense backwards. The rate of change of v sub x of t is just dv sub x by dt. This is a constant, so the rate of change of a constant is 0, and then this is a constant times time. The rate of change of a constant times time is just that constant. So we got back what we started from. dv sub x by dt equals a sub x. Okay, one of our results is that v sub x is v sub x initial plus a sub x times time. I'm going to write that down more prominently up here. So we have the first result, which is v sub x is v sub x initial plus a sub x times time. Let's just write down a second copy of that and then integrate both sides. So we had v sub x equals vx initial, which is just a constant, plus a sub x times t, where a sub x is also a constant. Before we go on, let's just remember that the definition of v sub x is dx by dt. That's just a definition. So let's erase this and in its place write dx by dt. And then we want to integrate both sides. So we can integrate this side with respect to time from 0 to t. And then we'll put some parentheses here. And we'll integrate this with respect to time from 0 to t. This is just saying the integral of the derivative of x. So the integral of the derivative of x is just x. So this is x of t minus x initial. In other words, minus x at t equals 0. And then over here, this is just a constant. So when you integrate a constant, you just multiply by the variable you're integrating by. So this is vx initial times t. Okay, so this is a constant times t. Remember, if you integrate t, you get 1/2 t squared. So this is 1/2 a sub x t squared. This tells us x of t is x initial plus vx initial times time plus 1/2 a sub x t squared. This is one key result we get from constant acceleration, and this is another key result that we get from constant acceleration. So x of t is x initial plus vx initial times time plus 1/2 a sub x t squared. Now there's actually going to be one more result we can get by combining these two starred results. So let's see what that is. It turns out it's useful in problems where you don't care about the value of the time. If the acceleration in the x direction is constant, then v sub x is v sub x initial plus a sub x t, and x is x initial plus v sub x initial times t plus 1/2 a sub x t squared. You might have seen this if you took an earlier physics course. You might have seen it without all the subscripts. You might have just said v is v naught plus a t, and you might have seen x is x naught plus v naught t plus 1/2 a t squared. Mazur's book does not use a subscript 0 for initial. It uses a subscript I for initial, and it's very careful to distinguish x components. So we'll use his notation. If you have a problem where you want to know the final velocity, so suppose you know the initial position and you know the final position, but don't care about the time. So you can use one of these equations to get the time and then eliminate the time. If we solve the first equation for the time, then this gives us that the time is v sub x minus v sub x initial divided by a sub x. Then we can use that for the time over here, and this gives us x equals x initial plus vx initial times vx minus vx initial over a sub x plus 1/2 a sub x, and then we have vx minus vx initial divided by a sub x all squared. And then I think we can do a little simplification. There we go. Whoa. See, this is why I don't ask you to do this kind of algebra. Then we get vx final squared is vx initial squared, because we move this over to the other side, plus 2 a sub x times x final minus x initial. Whoa, that was a lot of work. So let me just write that next to its friends. So it's this guy here. That's a result that's actually worth remembering and using, but it's not worth worrying about how to derive. I wanted to show you that so you see that all it is a result of taking this and solving it for time and plugging it into this, and then the cancellation is a little bit messy. Okay, so if you take the first one, solve for t, plug it into the second one, you get this result, which is often very useful if you don't care about the time. Vx final squared equals vx initial squared plus 2 a sub x times x final minus x initial. One place this last result is helpful is like, suppose you drop a ball, you drop a steel ball, and you want to know how fast is the ball traveling at the instant right before it hits the ground. I know since I dropped it, it had 0 speed when I first dropped it. I know acceleration is just minus g. I know just before it reached the ground how high it is. I know how high it was when I dropped it. Then I want to know what's the speed right before it reached the ground. So if you don't care about the time, you just want to relate the change in position to the change in speed, then this result is very helpful. It can save you some time to remember it. And again, my point here is just that these equations are simply the result of taking acceleration in the x direction is constant and doing a little bit of math. You don't have to remember how to do that math, but I just want you to know that there's no magic. It's just this assumption plus a little bit of math. It turns out that falling to the ground at a downward acceleration of g happens so quickly that it can be difficult to see exactly what is happening. And that, I guess, was especially true with the limitations of technology hundreds of years ago. We didn't have smartphones with slow-mo recording. So the question is there a way to fall in slow motion so that you can see a little more with the unaided eye what is happening? And it turns out there is. We can slide down a hill. If we slide down a hill, then instead of just this value g, we actually multiply g by the sine of the incline angle of the hill. And you don't actually have to remember any trigonometry at this point in the course. You just have to be able to just recognize this drawing. If we have an inclined plane whose angle with respect to the horizontal is theta, in Mazur's convention we define the x-axis to point downhill. So x equals 0 is at the top of the hill, and x gets bigger and bigger and bigger as you go down the hill. So on an inclined plane we have a sub x equals plus g sine theta. It makes sense that it's plus because you know the object is going to accelerate downhill, and we have x points downhill. And by contrast with free fall, we have x pointing up. So free fall in 1D, one dimension, we have a sub x equals minus g and x points upward, straight up. Okay, so these are the two situations that we're going to use again and again in chapter 3 problems. So we have constant downhill acceleration of magnitude g sine theta for an inclined plane, and we have constant downward acceleration of magnitude g for free fall near Earth's surface. So to look at this situation a little more carefully, or to see it with your unaided eye, and we'll also see it with the eye of a computer, we're going to use a contraption called an air track, which is kind of like an air hockey table. You imagine you take an air hockey table and you tilt one end of it upward a little bit so that the puck wants to slide. Then we're going to call the top end of it x equals 0, and we'll call the bottom end of it x equals about 2 meters. And let's look at a video of how that works. This is like an air hockey track where air comes up through these little holes and it eliminates the friction. An air hockey track would be eliminating the friction between the table and the puck. Here we're eliminating the friction between the track and this cart. This track is inclined at a small angle, and as I do this, I'm going to turn on an air pump, which will make a lot of noise, and it will reduce this friction. I'll also start a graph going so you can sort of see the motion on the graph. That seems pretty good. Okay, we have things set up in such a way that this is x equals 0, and then we get down to the bottom end of the track, and it's approximately x equals plus 2 meters. Then we're making graphs of the position versus time and the velocity versus time. Our acceleration, a sub x, is positive in the downhill direction. X points downhill, so a sub x is plus g sine theta. If we made theta bigger, the acceleration would be bigger. I think you might be able to see that, at least with your eye, if we just momentarily make the slope a little bigger. Okay, we could try that one more time. Okay, so that's a bigger acceleration because it's a bigger theta, so it's a bigger sine theta. And then we'll go back to the smaller theta. So this is small enough that it's pretty easy to see. So we travel downhill from x equals 0 to x equals approximately 2 meters. Let's look at these 4 graphs and see which one you think shows the expected shape of x of t, which is in yellow, and of v sub x of t, which is in light blue, if I release the cart at rest. I release the cart at rest from x equals 0. So x would start at 0, and I guess the cart goes downhill. I release it from rest. And remember, the x-axis in this problem points downhill. This is x equals 0, and this is x around 2 meters. So if you look at that picture of the cart released from the top, so it's released from x equals 0, and it's released at rest. So initially the speed is 0, and then it accelerates downhill. So what do you expect x as a function of time to look like, and what do you expect v sub x as a function of time to look like? So I guess I expect x to start at 0 and then to wind up near x equals 2 meters. Let's see if that's true in all these cases. So in graph A, x does start at 0 and x does end at 2 meters. So far so good. In B, x does start at 0 and x does end near 2 meters. So far so good. In C, x starts at 0 but it ends at negative 2 meters. So that seems to contradict our coordinate system. And in D, x starts at 0 and it ends around negative 2 meters. So I think C and D both contradict our coordinate system. So I think we can rule those out. So now it's between A and B. And I think the x versus t curves look the same in A and B. It's just the velocity curves that are different. Here in A, the velocity starts out at 0 and becomes negative. And in B, the velocity starts out in 0 and becomes positive. We said that the downhill direction is positive x, and we said that a sub x is plus g sine theta, so it should be some small positive number. And remember, a sub x is the rate of change of v sub x. And also remember that we should see that v sub x should be the initial value of v sub x plus a sub xt, and a sub x is positive. So we should see v sub x is v sub x initial plus this small positive number times time. So I think we expect that the velocity starts at 0 because we just let the cart go with 0 speed. And I think we should see that the velocity gets bigger and bigger and bigger, more and more positive, because more and more downhill speed means more and more positive velocity with our coordinate system having the x-axis point downhill. So I think I like B. Bravo.
If I simply release the cart from rest, then initially its speed is 0, so its velocity is 0, and then it goes faster and faster and faster and faster, it's speeding up. But in particular, its velocity becomes more and more positive, because this is the downhill direction. That's the positive x direction. The velocity in the x direction is 0, and then it's positive, and it's bigger and bigger and bigger and bigger. And we can see a graph of that. Meanwhile, the x-coordinate itself, which is the downhill coordinate, is 0 here. It's becoming positive, more and more positive, but it's becoming positive at a higher and higher rate. So now let me try something a little different. If I give the cart a shove, initially the cart is moving that way, and then it turns around and moves back this way. So initially its velocity points uphill, but the x-axis points downhill. And then it seems like it slows down. It's going to start going quickly uphill, and then it goes less and less quickly uphill, and that's going downhill and more quickly downhill. So here's uphill, less and less quickly, now downhill, more and more quickly. Now remember, the x-axis points downhill. So is v sub x negative or positive when I first shove it? I mean, just after I release it. Is this negative or is this positive v sub x? Think about that. And then it seems like the magnitude of the velocity, the speed, is big here, and it gets smaller and smaller, and then it turns around to 0 magnitude, and now it's bigger and bigger magnitude. So think about the velocity versus time here. Oh, that was perfect.
Suppose I shove the cart upward starting from x equals 2 meters. So I start at x equals 2 meters at the bottom of the track. I give the cart an upward shove. It goes up, and it turns around, and it comes back down. Initially, x is around plus 2 meters. It makes its way up almost to x equals 0, and it comes back, and at the end, it's around x equals 2 meters again. I think x should start out around plus 2 meters, and it should find its way down close to x equals 0, and then it should find its way back up close to x equals 2 meters. And then, well, what should it look like? Let's think about that in a minute. And then v sub x versus time. Well, I start the car at the bottom of the track, which is x around 2 meters, and I give it a shove uphill. Since the x-axis points downhill, if it's moving uphill, it must have a negative x velocity. So it somehow must have a negative x component of velocity. And then meanwhile, when I first shove it, then there's something complicated happening. But then after I release it, it's just acting under the influence of gravity until either I catch it or it crashes into an endpoint. So it should have a positive slope after that. And also it should have a positive constant slope. So I should really be very careful to draw this as a straight line. And then another thing to notice is at the point where the slope is 0. Remember, the slope of a curve is 0, where that curve is at a maximum or minimum, if you like calculus. So I think the maximum or minimum is going to be here, and then it's going to have a big negative slope here, 0 slope here, and a big positive slope here. But that's not a very nice looking, this really should be a nice quadratic curve. Let me make this a nicer quadratic looking curve. So I think this should look like a smiley face like that. So we have a big negative slope here, 0 slope here. That's the same point in time. And we have a big positive slope here. So I think we expect something that looks like that. So here's 0, there's positive, here's 0, here's positive, here's negative. Let's see if any of these curves look like that. See, this goes from minus 2 meters to 0 and back up. So that's no good. Minus 2 meters towards 0 and back up. That's no good. Here's plus 2 meters towards 0 and back up. That seems pretty good. Plus 2 meters towards 0 and back up. I think I like either C or D for the position versus time curve. And then I think the velocity should start out negative and it should have a positive slope. You see, it starts out positive, it has a negative slope. But we want to start out negative and we want a positive slope. So I think I like D here, delta. So it seems like this curve D, delta, is the only one that makes sense because the x coordinate starts out at 2 meters and it gets smaller and then it gets bigger. And the velocity starts out negative and it crosses through 0 and it gets more and more positive and it has this constant positive slope. So that seems good to me. So I think I like option D, delta there.
And now let's run the graph and see what happens. Let's try it one more time. So I shove it uphill, and then it comes back downhill. So if I give the cart a shove uphill, and I watch it travel up and back, and remember the x-axis points downhill, at the top of the cart's trajectory, where it turns around, what is the value of the x component of velocity? Here, at this point, at this point, or at this point, or at this point, what is the x component of velocity?
I shove the cart uphill and I watch it travel up and back. We define the x-axis to point downhill. At the top of the cart's trajectory where the cart turns around, what is the value of v sub x? Remember, we had the x versus t curve look like this. It goes from plus down to 0, back up to plus x versus t. Then remember that we had the vx versus t curve look like this. So it started out negative and it went up to plus, and this is the point where it turns around. So the point where it turns around is here. So that's at its minimum value of x. And I say at that instant v sub x equals 0. So the slope of the x versus t curve is 0 at that point where it turns around because it's at a local minimum. And so v sub x equals 0. Notice the acceleration is constant, but at this instant v sub x passes through 0. Now, by the way, I guess I just gave it away. At that instant where the cart turns around, what is a sub x? Think for a minute. But notice, as the cart was going uphill, v sub x was negative and it was becoming less and less negative. Then as the cart goes back downhill, v sub x is positive, it's becoming more and more positive. This slope has not changed. This is the same slope. Over here, just before it crosses 0, v sub x is negative and it's becoming less negative. Just after it crosses 0, v sub x is positive and it's becoming more positive. But the slope hasn't changed. And remember that a sub x is just dv sub x by dt. So the acceleration is just the slope of this velocity versus time curve. And the slope of this velocity versus time curve is a constant positive value from the instant just after I shove it until the instant just before I catch it. So I think the answer is positive. So a sub x is still positive g sine theta at that instant. So I think, yeah, it's not negative because this is a positive slope. It's not 0 because this is a positive slope. It's not infinite or undefined. I think it's positive. So a sub x is positive. So I think I like this answer.
Let's watch the graphs one more time. This point. So if we look at the graphs that we just made, then the place where I said this, the x component of velocity was 0. So I shoved it upward. So we had a negative x component of velocity because it's going uphill and the x-axis is pointing downward. Then the velocity x component is becoming less and less and less and less negative. At the point where it turns around, the x component of velocity is 0, and now the velocity becomes positive and more and more and more and more positive. But notice that the slope of the velocity curve, especially if you look at the graph that we made with the computer, is constant. And the slope of the velocity curve, slope of the v sub x versus t curve, is a sub x. The rate of change with respect to time of the x component of velocity equals the x component of acceleration. So what is the acceleration at this point? Well, I say at that point that we pointed to, the x component of acceleration was the same plus g sine theta. You might be tempted to say that the acceleration is 0 here. It's not. The acceleration as it's turning around is the same as the acceleration just before it turned around, is the same as the acceleration just after it turns around. And you can see that by noticing that the slope of the velocity versus time curve does not change there. It changes abruptly as I shove it, and it changes abruptly as I catch it. But from the time I release it to the time the cart comes back, the slope of the x component of velocity versus time curve is constant. So the acceleration is this constant. That's a really key point. One more scenario. What do you expect the shape of the position versus time, x of t, and the x component of velocity versus t, v sub x versus t, to look like if I start at x equals 0 and I give the cart a gentle shove downhill? This is x equals 0. So if I give it a downhill shove like this, remember earlier I just released the cart from x equals 0. Instead I want to give it a downhill shove from x equals 0. So I'm starting it with a shove like that. What do you expect the x component of velocity versus time to look like? And then also, what do you expect the position versus time to look like? The position starts out here, which is x equals 0, and I guess it gets bigger and bigger, more and more and more positive. What about the x component of velocity? Also, what is the shape of that position versus time curve?
Again, on the inclined air track, expected shape of x of t in yellow and v sub x of t in light blue if I shove the cart gently downward starting at the top. So I start out at the top at x close to 0 and I give the cart a downhill shove. So if I give the cart a downhill shove, its velocity starts out pointing downhill and then its velocity gets bigger and bigger and bigger in the downhill direction. And I guess it starts out at x close to 0 and x gets bigger and bigger. Well, again, the initial condition is that I give it a shove downhill, so it's a downhill velocity. Downhill is positive, so it's a positive velocity. So I think if we're going to draw v sub x versus time, it starts out positive. And remember, for the inclined plane, a sub x is plus g sine theta, and that is the rate of change of v sub x. So I think this is going to start out positive and get more and more and more positive. And then if we look at x versus t, it'll start out close to 0, but then it's going to get positive, and it's going to get positive at a bigger and bigger and bigger rate. It's going to start out a little bit above 0 and with a positive slope because it starts out with v sub x bigger than 0. That means the slope of this curve will be positive, and the slope of this curve will get more and more and more positive, like that. So which one of these looks like that? that? Let's see. Here's position going from 0 to positive. Here the position decreases and then increases. I don't think that makes sense. I don't like B because the position starts out decreasing and then increasing. I don't think I like C either because the slope starts out close to 0. And I think this slope should start out positive because we gave it a shove downhill. We didn't just let it go. We gave it a shove. So I think that leaves alpha and delta as options. This one, delta D, has a constant velocity. So the velocity is just always, it's like flatlined at some small positive value. That doesn't make sense because we know the track is inclined. So the velocity should increase. There should be a positive change in velocity each unit time. So I don't like D because it seems like it's constant velocity. Constant velocity is incompatible with being on this inclined air track. I think the only one left is A, alpha. So here the velocity starts out positive and it gets more and more positive. That looks like what we drew. And here the position versus time starts out with a positive slope and the slope becomes more and more positive and starts out a little above 0, maybe right around 0, and it goes away from 0 with a bigger and bigger slope. I think I like A, alpha, this selection, this guy. By the way, in class a couple years ago, somebody asked an excellent question after class about the difference in that previous slide between scenario A, alpha, and scenario C, Charlie. Let's look more closely at the difference between A and C. In C, the velocity starts out at 0 and increases. Here, the velocity starts out positive and increases. Here, the slope of the x versus time curve starts out 0. It starts out, you see the tangent of that curve is horizontal, and then it gets more and more and more positive. Here, the tangent of that curve starts out with a positive slope, and it gets more and more and more positive. So A and C look pretty similar, but C is what I would get if I simply let my fingers release the cart from the top without shoving it. Whereas A is what I get if up at the top I actually shove the cart downhill, so that at time 0, its velocity is positive, whereas if I just release it gently, then at time 0, its velocity is 0. So there's a subtle difference between releasing it from the top versus shoving it downhill. That was a really good question from a couple years ago.
Instead of just letting it go like this, I'm going to start it out with a downhill shove like that. That was pretty good. I like that one. What do you expect the shapes of x versus time and v sub x versus time to look like for a basketball tossed upward? And I'll just toss it upward from here and I'll catch it. We'll call time equals 0 the instant just after I release the ball, and then you want to know what happens from the instant just after I release the ball until the instant just before I catch the ball. And I claim during that whole time, from just after I release the ball until just before I catch the ball, the only influence acting on the ball is Earth's gravity. So during that time, from just after the instant just after I release the ball until the instant just before I catch the ball, the acceleration is downward, and again we have the x-axis pointing up, so a sub x equals minus g.
What are the expected shapes of x of t in yellow and v sub x of t in light blue? So remember, x is the vertical coordinate, so x equals 0 should be near the ground, and as we go up, x gets bigger and bigger in these one-dimensional free fall problems. V sub x is the velocity in the x direction. That's the x component of velocity. And remember, the acceleration is downward at g, so a sub x is minus g in free fall problems in one dimension near Earth's surface. So what do we expect? We want to draw x versus t, and we somehow start out near ground level. So this will be 0, and this will be positive values. It goes up to higher, more positive values, and somehow it comes back down. And let's think about the rest of the details of that shape in a moment. And then we have v sub x, the x component of velocity, versus time. Now, just after I release the ball, it has a big upward velocity. Upward means positive v sub x. At some point, it reaches its apex. At that instant, its velocity must be 0 because its height is a maximum and it is going from moving upward to moving downward. So at that brief instant, its velocity is 0. Then it's going downward at a bigger and bigger speed. So I think v sub x versus t looks like this, and this slope is minus g. So here's a positive value, here's 0, here's the negative value. And now we can be a little informed by this blue curve in drawing the yellow curve. We want a large positive slope here. We want 0 slope at this instant. We want a large negative slope here, so we can draw our quadratic shape to look like that. So the key is the slope is 0 up here, the slope is positive and big down here, and the slope is negative and large magnitude down here. And the slope gets smaller and smaller and smaller, and again the slope gets smaller and smaller and smaller. So the slope gets less and less and less positive, and the slope gets more and more and more negative. So let's draw it like that. See, this point, the local maximum, corresponds to this point where the slope is 0. Now, who looks like that? Well, B doesn't look like that because it's smiling instead of frowning. And D doesn't look like that because it's smiling instead of frowning. So I guess it's either A or C. Here, the slope of the velocity curve is downward. That's what we want. Upward doesn't make sense. So the only one that could make sense is C. Let's just look more closely at C. So the position goes from 0 to a positive peak and then back down near 0. That makes sense to me. The x component of velocity goes from a positive value, passes through 0, and goes to more and more and more negative values. That makes sense to me also. So I think I like C, Charlie, for this case.
At the very top of the basketball's trajectory, at this point, what is the value of v sub x at this point, So stop for just a moment, think. I say v sub x is 0 at that point. And then, at that same point, at this point, what is a sub x? Well, a sub x is the slope of this v sub x versus time curve. I say this slope is still minus g. Here it's minus g, here it's minus g, here it's minus g, here it's minus g, here it's minus g. Now you say, well, what if you could look in time, like a little bit before I threw it, or a little bit after I caught it? Then something different would be happening, because somehow my hand is abruptly changing the ball's velocity. But from the instant just after I release it until the instant just before I catch it, the acceleration is a constant minus g.
For that basketball tossed upward, what are the values of v sub x and a sub x at the top of the basketball's trajectory, assuming the x-axis points upward? Remember that we have definitions. V sub x is dx by dt. A sub x is dv sub x by dt. V sub x is the slope of the x versus t curve, and a sub x is the slope of the v sub x versus t curve. At the top of the basketball's trajectory, the only influence is Earth's gravity, so it should still be true that a sub x is minus g. So I think I expect a sub x to be minus 9.8 meters per second squared. On the other hand, at the top of the trajectory, just an instant earlier, it was moving upward. An instant later, it will be moving downward. At that instant, it's moving neither upward nor downward. So at that instant, its velocity is 0. So I think that at this instant, this represents the top of the trajectory for the basketball. At this instant, we have v sub x, which is dx by dt, is 0. But at that same instant, we have a sub x, which is dv sub x by dt, is minus little g. So I think I like this answer. Charlie. V sub x equals 0 because it's at a local maximum in position, but a sub x is minus 9.8 meters per second squared because it's still acting under Earth's gravity. The slope of this v sub x versus t curve has not changed. The value of the curve passed through 0, but the slope doesn't change. The slope just before this is the same as the slope just after this. It's just that the curve happens to pass through 0.
Let's make one more set of graphs, this time with the basketball. Instead of simply dropping it, we want to take the basketball and give it a downward shove at t equals 0. So t equals 0, shove downwards. So sort of like we did with the cart going downhill. Except remember, for the basketball, the x-axis points up. So we're going to start the basketball downward with a downward shove, and we want to figure out what the velocity versus time and the position versus time graph look like in that situation.
Okay, let's think about a basketball thrown downward. So if you stand up high and you release an object with a downward shove, in the absence of air resistance, the motion after release but before hitting the ground is best described by, okay, so while I'm shoving it, something complicated is happening, but as soon as I release it, the whole point of my shoving it is to give it a big downward velocity. So I give it an initial downward velocity. So let's just look at v sub x versus time. I'm giving it a downward shove. So at time 0, it must have a negative x component of velocity. And then if it's only under the influence of Earth's gravity, then the slope of that v sub x versus t curve is negative, which is saying that Earth's gravity is accelerating it downward, which is to say that v sub x is getting more and more and more negative. Every instant of time, v sub x changes in a negative way. I think v sub x starts out a little bit negative and gets more and more and more negative until just before it hits the ground. Meanwhile, what's the slope of this curve? Well, I think the slope of this curve, which by the way is a sub x, is minus g. I would say v sub x is always less than 0 and a sub x is minus g. So I don't like b because a sub x is certainly not 0. And I don't like c because v sub x is certainly not 0. It's moving downward and then it's moving downward more and more and more quickly. I don't like d for the same reason. So I think I like a here. Alpha. V sub x is less than 0 and a sub x is minus 9.8 meters per second squared. Okay, I'm going to drop a basketball from 2 or 3 meters in the air and I'll let it bounce twice before I catch it and see if you can imagine what a graph would look like of v sub x versus t. So that's the x component of velocity versus time, and a graph of a sub x versus t. So that's the x component of acceleration versus time, spanning the time from release to catch. So I release it and it bounces and it bounces and then I catch it. And again, the x-axis will point upward for projectile motion problems in one dimension. Don't worry about numerical values, but you want to be clear about positive values, 0, negative values, and maybe even which values are more negative than others. And we're going to do something similar in class with your group, but let's see if we can think it through on our own first as you watch me drop the ball.
Let's take a basketball and let's say I hold it at a height of about 2 meters and then drop it and I'll let it bounce twice and then I'll catch it. Let's just do that so we have the real video that we can then make a graph of. Do it again. Okay, so I let go of the basketball and it fell under Earth's gravitational force and it bounced. And remember, after it bounced, it didn't make it up to quite the height I dropped it from because in the bounce it lost some energy. And then I didn't touch it, it bounced again and it came back up again, not quite to as high as it did on the first bounce, and then I caught it. So let's look at the vertical position. I think I'm going to try to make one big set of axes and draw everything on one big set of axes this time. So here is time. And we're going to start out, this will be the vertical coordinate, y. There's y versus t. We started out some height above the ground. I held it above my head, let's say that's 2 meters. So we didn't really put numbers on the graph. Let's say that's 2 meters. So I'm holding the ball up here at y equals 2 meters. and I'm holding it for a while, so it stays that way for a little bit. And then I let go. Now, this is something you probably would have had to puzzle over with your group mates. And so I think the best way to understand this is when we actually draw the velocity graph. It's going to turn out that this is an arc of a parabola. The ball, initially, I just let go of it, and it starts out with 0 speed, and the speed gets bigger and bigger and bigger and bigger, and the speed is maximum just before it hits the ground. That corresponds to the slope of this graph. The slope starts out 0, and the slope gets bigger and bigger and bigger and bigger and bigger until it hits the ground. And then the ball bounces. So it's basically going to retrace the same motion. If the collision with the ground lost no energy, if it were a 100% elastic collision with the ground, then this would just be a mirror image. But it actually lost some energy in the bounce. You can tell it didn't go up quite as high. So it's not quite going to be a mirror image. It'll be kind of a shrunken mirror image. So it's going to go back up like this, but to a lower height. And this is the instant, you can see when the slope becomes 0, that's the instant when it's at the apex of its orbit, and then it's going to go back down like this, and then it's going to bounce up again, and again it'll reach not quite as large a height. And then this is where I caught it, so then I catch it here. So I release it here. Here's the first bounce, here's the second bounce, I catch it. And so it's really important that this height is lower than the original height because that was what we saw. There's some loss in height between the top of its motion when it first bounces and when I first released it, and there's some loss in height between the top of its motion after the second bounce and when I released it. Then we can try to look at the velocity. Let's look at the vertical velocity versus time. Okay, so we'll call that v sub y. So I'll draw that in this orange color. The vertical velocity here is 0. You can see why I'm not an architect. The slope of this thing, it starts out 0 and it gets negative and it's more and more and more and more negative. So this is actually sloping down. So it starts out 0, but it's negative and it gets more and more negative. So it's kind of like that. And it's most negative, so the velocity is the largest downward just before it bounces. And then after it bounces, if it bounced with no loss of energy, then its speed, so speed is the absolute value of the velocity, the magnitude. So if it bounced without losing any energy, the speed immediately after would just be the opposite. It would be it would be the same magnitude, but on the upper side of the axis. But it actually bounced with a little bit less. It lost some energy, so it actually has an upward velocity which is a little bit smaller than the downward velocity just before it bounced. So it's something like that. This slope, by the way, is minus g, where by g I mean 9.8 meters per second, or in old-fashioned units 32 feet per second. So that same slope is going to be the slope here, because that just represents the fact that the only force acting on the basketball is gravity, or ignoring air resistance. So I want to draw that same slope. We're going to go down with that same slope, and see it crosses through 0 here. That makes sense, because this is where it's highest in the air, and at the point where it's highest in the air, it's momentarily at 0 velocity, just for an instant, and now it keeps going down like that. So that makes sense. See, here it has an upward velocity, which is big, and it's a smaller and smaller and smaller upward velocity. At this instant, it has 0 velocity, and then it's negative velocity. It's a bigger and bigger and bigger negative velocity. Now it bounces again, and we want to make sure that this goes up a little bit less than that to represent that sort of loss in energy. If I really want to do this perfectly, I think I exaggerated this difference in velocities, and I'm exaggerating it here even more. I'll explain that in a second. This is beyond, you don't have to be that subtle. Then we did something like this, and then I catch it, so now the velocity is 0. So again, here the slope is minus g, and here this slope is minus g, because these are the periods when it's entirely under the influence of gravity, nothing else. And then, see, there's a big positive slope here, which is the elastic force. This is when the basketball is decompressing. Well, actually, it's compressing and then decompressing. So then if we draw the vertical acceleration so this vertical velocity, again, was dy by dt, and this vertical acceleration was the velocity y by dt. So the slope here is 0, and so it's basically the slope of this curve. So that's fine, it's just like that. And then we have something that's minus g. I'm going to make minus g be kind of small here because okay, so that's fine. And see, over here the slope is also minus g, and over here the slope is also minus g, and then the slope is 0 of the orange curve, because the purple curve is the slope of the orange curve. Now the thing is, notice that we pretty abruptly go from a negative velocity to a positive velocity. So in order to do that, for a short time, you need a very big positive acceleration. So if you were an ant riding on the basketball, you would find that instant when the ball bounces quite uncomfortable, as if you were in a pretty rough amusement park ride. So here the slope is minus g, so the acceleration is minus g. Here the acceleration is some much bigger than g in magnitude, positive number. Here it's, again, negative g. And here it's, again, this much bigger than g positive number. And here it's minus g. Let's sum up the results to date. Velocity is the rate of change of position. So v sub x is dx by dt. Acceleration is the rate of change of velocity. So a sub x is dv sub x by dt. If acceleration is constant, and we're in one dimension now, so if the acceleration in the x dimension is constant, then we can work out, using a little bit of math, that vx final equals vx initial plus a sub x times time. And x final is x initial plus vx initial times time plus 1/2 a sub x times time squared. So x final is x initial plus vx initial t plus 1/2 a sub x t squared. And then if you combine these two
and eliminate the time, you can get that Vx final squared equals Vx initial squared plus 2 times a sub x times x final minus x initial. So Vx final squared is Vx initial squared plus 2 times a sub x times x final minus x initial. Okay, and the two important cases so far for which a sub x is a constant, so where we have constant acceleration in the x direction, we have free fall near Earth's surface where a sub x is minus g. So the x-axis points upward and the acceleration is g straight downward. And the other is an inclined plane where the x-axis points downhill and a sub x is downhill and it's smaller than g because it's just a downhill part. So a sub x is g sine theta with a plus sign. Okay, so we're going to work some examples where we make use of these results. If I stand h equals 20 meters above the ground and I release a steel ball from rest, how long does it take the steel ball to reach the ground? Okay, if you want to use g as approximately 10 meters per second squared, that makes the math a little easier. We'll see whether we need to do that or not. Okay, how long does it take to reach the ground? We know x initial is h, and we know that x final is 0. 0 is ground level. H is h meters above the ground. And we know that Vx initial is 0 because we simply release it from rest. We don't shove it. Okay, we want to know how long it takes to reach the ground. I think we can use this result. So we'll say x final is x initial plus Vx initial t plus 1/2 a t squared. And we know that a sub x is minus g. This is 0. We know that this is h and this is 0. And this is actually minus because a sub x is minus g. So this is minus 1/2 gt squared. So I guess we have only two terms left. This tells us 2h equals gt squared. So t is 2h over g, the square root of. Okay, we have t is the square root of 2h over g, which equals the square root of 2 times 20 meters divided by 9.8 meters per second squared. So if we were to use g equals 10 instead of 9.8 to make the math easier, we'd say 2 times 20 divided by 10. 2 times 20 is 40. 40 divided by 10 is 4. Square root of 4 is 2. So that's 2 seconds. So this is approximately 2 seconds. So I like answer A, that it is approximately 2 seconds. Okay, you could do it more carefully by using 9.8 instead of 10. If you use 9.8, you'll get a number just slightly bigger than 2 seconds. Maybe you'll get like 2.01 seconds. So that was our first problem that we worked together using numbers. If I stand 20 meters above the ground and I release a steel ball from rest, what is its velocity the instant just before it reaches the ground? If we just solved for time in the previous question, on the previous slide, we know the time is about 2 seconds. If we know that, then we can say Vx final is Vx initial plus a sub x t. So we know Vx final, and then Vx initial was 0, and a sub x was minus g. So there's minus gt. So 0 minus gt. So this is minus, and this is 9.8, or it could be 10 meters per second squared, and then we had about 2 seconds. So it seems like the answer is going to be Vx final is pretty close to minus 20 meters per second. I think I like that. 20 meters per second pointing downward. Now, you might not have remembered the answer to t from the previous slide. If you don't remember the answer to t from the previous slide, or maybe for whatever reason you didn't work out the time, this is a brand new problem maybe and you didn't work out the time, then we can say Vx final squared equals Vx initial squared plus 2 a sub x, x final minus x initial. Okay, so Vx final is unknown. Vx initial is 0 because we just released it from rest. And then a sub x is minus g. So this is plus 2. And then this is minus g, and then x final is 0, and x initial is h. So the two minus signs cancel, and this 0 disappears. So we get Vx final squared equals 2gh. Vx final is plus or minus the square root of 2gh. So that's plus or minus the square root of 2, and then we could say 10, but the 9.8 meters per second squared, and then 20 meters. 2 times 10 is 20 times 20, that's 20 times 20. The square root of 20 times 20 is 20. I mean, 20 times 20 is 400, square root of 400 is 20, but you see this is 20 times 20. So square root of 20 times 20 is just 20. The answer is plus or minus 20 meters per second. So this equation, if you use this equation, V final squared is V initial squared plus 2a delta x, it doesn't give you a sign. You have to work out the sign. So you know that if you release it from rest, then when it gets to the ground, it's moving downward. Since our x-axis points upward for these problems and it's moving downward, that must be a negative velocity. That gives you Vx final is like minus 20 meters per second. So same answer, we got it a different way. It's always good to try something more than one way and see if you get compatible answers. A box is at the lower end of a frictionless ramp whose length is L equals 10 meters. And the ramp makes a non-zero angle 30 degrees with the horizontal. This sounds like an inclined plane problem. A worker wants to give the box a shove so that it just reaches the top of the ramp. How fast must the box be going immediately after the shove, which is assumed to be an instantaneous shove, like a kick, in order for the box to reach its goal? Okay, and then we can remember some math stuff. So we have an inclined plane here. Theta is 30 degrees, and then this length, this is x equals 0. This is x equals L, which is 10 meters, and the x-axis points downhill. We have x initial is L, which is 10 meters, and we have x final is 0 because we want it just to reach the top of the ramp, which is x equals 0. We also know that when we get to the top of the ramp, Vx final is 0 because we say it's just barely able to reach it. So it's going to go up with, shove it upward, and it goes less and less and less and less quickly, and it's going to just reach the top. So its speed is going to be 0 at the top because that's what we mean by it just barely reached it. And then Vx initial is something we're trying to figure out. And then we know that a sub x is plus g sine theta. By the way, sine of 30 degrees is 1/2. So that's kind of a useful fact. So then this is pretty darn close to plus 5 meters per second squared. Okay, so for this problem, because g is a little bit less than 10 meters per second squared, and sine theta equals 1/2. So let's just say a sub x is plus 5 meters per second squared. We don't care about the time in this problem. So we know the final speed. We want to solve for the initial speed, and we know the initial and final positions. So it seems like this is an excellent occasion to use this v final squared is v initial squared plus 2a delta x equation. So let's do that. So Vx final squared, that's 0. Let me just copy down the equation so we know what we're plugging into. Vx final squared equals Vx initial squared plus 2ax x final minus x initial. Okay, now let's substitute. So this is 0, is unknown, Vx initial squared plus 2. What is a sub x? A sub x is plus 5 meters per second squared. X final is 0, and x initial is L, which is 10 meters. Okay, and this is very convenient, so the 0 drops out and we get minus 10, so this is a negative thing, so we can bring it over to the other side. So it seems like we're going to have 2 times 5 is 10, times 10 is 100. 100 meters squared per second squared equals Vx initial squared. That leaves us with Vx initial is, well, so now you have to get the sign right. When you use this equation, you have to figure out the sign intuitively, but we know it's traveling uphill. It's negative. So Vx initial is negative 10 meters per second. There you go. Oh, well, how fast? Okay, so how fast is the speed? So the speed has to be 10 meters per second, but it's 10 meters per second uphill. So the velocity is minus 10 meters per second in the x direction, but the speed is 10 meters per second. So how fast is basically the speed? Okay, so I think I like that. I like answer delta. Okay, now let's extend that same problem. So we're going to start with the same scenario, except we worked out that its initial speed was 10 meters per second. In fact, it's uphill, so if we care about the sign, then Vx initial is minus 10 meters per second. We can actually use the same equation to figure out how fast is it going when it's halfway up the ramp. Yeah, what is the box's speed when it's halfway up the ramp? Now, you might be tempted to say, oh, halfway up the ramp must be half of the time. That's not right, because halfway up is not half the time because it's not moving at a constant velocity. So halfway up is not half the time. Anyway, we don't know the time in this problem anyway. We'd have to work out the time separately. But anyway, that would get a wrong answer if you did that. Sometimes it's useful to think about ways you could do it incorrectly. So let's use the same equation, but now we want to go halfway up the ramp. Now x final is L over 2, and Vx final is unknown. So we're going to say Vx final squared is, so Vx initial squared, so that's minus 10 meters per second, the quantity squared, plus 2 times a sub x times, and then x final was L over 2, and x initial is L. So then we can say, oh, and this is squared. Ha! Vx final squared is 100 meters squared per second squared plus 2. Here's 5 meters per second squared, and then this L over 2 minus L is minus 5 meters. There we go. So we have meters squared per second squared, meters squared per second squared. Also, when you square minus 10, you get plus. So there's 100 meters squared per second squared minus 50 meters squared per second squared. So this is 50 meters squared per second squared. Vx final, and it's moving uphill, so it's approximately minus 7 meters per second. 7 squared would be 49, might be 7.07. That's its velocity, is minus 7 meters per second in the x direction. So 7 meters per second in the minus x direction. So its speed is the magnitude of its velocity. So its speed is 7 meters per second. There we go. Its speed when it's halfway up the ramp is 7 meters per second. You saw me start to make a few mistakes, which I then caught. You see, it's really important to try to do things different ways. It's also important if you're working with somebody else to do your calculations in parallel and check your final answers together, because you and your friend are not likely to make the same careless mistake. So you might make one mistake, your friend might make a different one. You might work through problem 1 perfectly, your friend might work through problem 2 perfectly, and so then if you compare your answers, and if you disagree, you actually track it down, then you'll learn something and you'll be much less likely to write down a careless mistake. I have to catch my own mistakes here. So I think I like that. I like it's about 7 meters per second. By the way, Wolfram Alpha will solve quadratic equations for you. For instance, if you says 47t plus 5.3t squared equals 20.
Just as some random example of a quadratic equation.
But if you don't want to solve quadratic equations, you want to let the computer do it for you, you can just type a quadratic equation into Wolfram Alpha, and it will not only give you a solution, but it will often give you a graph also. So before we wrap up, let's talk about some potential sources of confusion from Chapter 3 based on responses from previous year students reading this chapter. Inclined planes are new to many people. Don't think that you have to do a lot of trigonometry to do inclined planes. You just have to recognize that theta is the angle of the inclination, and you just have to use the sine function. By the way, remember that the sine function on your calculator will get different answers depending on whether you're in degrees mode or radians mode. There's this thing called a motion diagram that will appear in Chapter 3. I actually don't draw motion diagrams, but sometimes, you can say, well, here's t equals 0, and here's t equals some later time. You might say, initially, I'm moving, and then I'm not moving. It's kind of like just a pictorial representation of like where are things before and after, and which direction are they moving in before and after. So you kind of sum up what you know about the motion in a diagram. Sometimes there's like following the reasoning about what's happening. So for instance, it actually is really important as you go through to reason through what's happening to the x component of velocity and what's happening to the x component of acceleration for like a basketball at the very top of its orbit when it's tossed upward. So I really urge you to puzzle through that and look at the graphs in the book and look at the graphs we drew earlier today. So there are like some mathy parts at the end of the chapter that are pretty hard to follow. So I tried to annotate the chapter so you know which things you can gloss over. And I think you can gloss over pretty much all the equations in the chapter if you just want to focus on the equations that we wrote down in this lecture. Then there is this checkpoint 3.6, which you have to stare at really closely if you want to figure it out. So figure 3.6b, this is x versus time. So this is like time step n, step 0, step 1, step 2, step 3, step 4. So here's step 1, step 2, step 3, step 4, step 5, step 6, step 7, step 8, step 9, step 10. So time step n, and then here's the x position. It's like on a film strip. And here's this clever trick. In drawing B here, you see what he's drawing here is x2 minus x1. And then this is x3 minus x2. And this is x4 minus x3. This is x5 minus x4. x6 minus x5, x7 minus x6, x8 minus x7, x9 minus x8, and x10 minus x9. Notice that each one of these intervals is an equal delta t because it's like a film strip moving at equal time intervals. So it's not really just delta x, it's really delta x divided by delta t. So it's kind of like velocity in the x direction. This is really like v sub x because it's like dx dt. So it's like delta x divided by delta t, which is basically the x component of velocity. So really what's being graphed here is the x component of velocity versus time, or at least something proportional to the x component of velocity versus time. Because you have to figure out what the time interval is in order to get the x-axis labeled correctly. But you're wondering, why is this a straight line? It's kind of tricky. It's a straight line because this delta x is really like delta x per unit time. So really what you're graphing on the vertical axis in figure 3.6b is dx by dt, or at least something proportional to dx by dt. So that's pretty tricky if you want to know why that worked out to be a straight line. Because the points are all equal steps in time, the quantity being graphed is proportional to v sub x, which is the x component of velocity. So it's kind of a bonus. I have one more thing here, which is going to be a variation on a worksheet problem that you'll work. So this might give your brain a head start at thinking about this worksheet problem that will come up. A rock dropped from the top of the building travels 21.5 meters in the last second before it hits the ground. Assume that air resistance is negligible. By the way, worksheet might ask something like how tall is the building, but let's go step by step. Which of the following statements is true? So again, let the x-axis point upward for projectile motion in one dimension. Is the rock's average velocity during the last 1 second of its fall minus 21.5 meters per second? So is that a true statement? Well, it travels 21.5 meters in the last second before it hits the ground. So I think you could say that x final minus x initial is dx average times t final minus t initial. I think that's a true statement because Vx average is just a change in x divided by the change in t. And the x-axis points upward, so x is decreasing. X is becoming less and less and less positive. So I think this is a true statement. A, is the rock's instantaneous velocity 1 second before it hits the ground minus 21.5 meters per second? I actually don't think so because you know the rock, as it falls, is falling faster and faster and faster and faster. So you know that its average velocity during the last 1 second of its fall is minus 21.5 meters per second. That means it must have been falling a little bit less quickly 1 second before it hits the ground, and a little bit more quickly than that the instant that it does hit the ground. I mean, actually, I guess it might turn out that its instantaneous velocity 1/2 second before it hits the ground is minus 21.5 meters per second. But it's certainly not true 1 second before it hits the ground. So I think that is a false statement. You could think about why that's true. The rock's instantaneous velocity, v sub x, at the instant just before it hits the ground is minus 21.5 meters per second. I think that's false also because I think the instant just before it hits the ground is actually moving faster than 21.5 meters per second. So see, because if its average velocity during that last 1 second of its travel is 21.5 meters per second downward, then it's moving downward at less than 21.5 meters per second 1 second before, and it's moving downward at more than 21.5 meters per second the instant just before it hits the ground. So I think that's also a wrong statement. And this certainly isn't true because B and C are false. And this certainly isn't true because A is true. So I think the only statement here that's true is A. That's worth pondering. A rock dropped from the top of a building travels 21.5 meters in the last second before it hits the ground. Assume that air resistance is negligible. And again, worksheet is probably going to ask you how tall is the building. At the instant just before hitting the ground, the rock's speed is, I think we just discussed this. I think it should be a little faster than 21.5 meters per second because as it falls downward, it's going to go downward faster and faster and faster and faster. If in this last interval, its average velocity is 21.5 meters per second downward, then just before it hits the ground, it must be going a little faster than 21.5 meters per second. So I think it's C, Charlie. So it's somewhat faster than 21.5 meters per second, the speed. By the way, the speed can't be negative, so you can rule out B because speed cannot be negative. That was kind of fun. A rock dropped from the top of a building travels 21.5 meters in the last second before it hits the ground. Assume that air resistance is negligible. Let the building height be h. Let the total time the rock falls be t. What is a true statement about the problem? H minus 1/2 gt squared equals 0. So it was dropped. When it says dropped, it doesn't mean thrown. It means just dropped, just released from rest. So I think this is a true statement because you could say x final is x initial plus dx initial t plus 1/2 a sub x t squared. X final is 0, x initial is h, vx initial is 0, and a sub x is minus g. So this is the same as this statement. What about 0 minus gt is minus 21.5 meters per second? I think we just ruled that out on a previous slide because this would say vx final equals vx initial plus a sub x t. So that's like vx final equals 0 minus gt. That is true. Vx final is 0 minus gt, but Vx final is not minus 21.5 meters per second. Vx final is probably going to be somewhat more negative than 21.5 meters per second. So this is wrong. Oh my goodness. H minus 1/2 g, t minus 1 second, all squared is 21.5 meters. I think that's true. This is saying, boy, this is really tricky. Let's plug in the time 1 second before it hits the ground. So that's saying 21.5 meters. That's the height 1 second before it hits the ground. And it started out at h, and it started out at 0 velocity. And then this is minus 1/2 g. And then what's the time? The time is t minus 1 second. So we plugged in t equals 1 second before it hits the ground. And we plugged in x equals 21.5 meters above the ground. That should be a true statement. So I like that. I think that's a true statement. What about, what in the world? I think I see what that's saying. So this should be saying vx final is vx initial minus gt. So here, if we write the vx final over here and erase this, then I think we have it in this form. This is saying, if you look at answer D here, it is trying to say that the instantaneous velocity 1 second before it hits the ground is 21.5 meters per second downward. We know that's a false statement. I mean, I actually think that statement is true a half second before it hits the ground. But 1 second before it hits the ground, I think it's moving less quickly than that. I think it's actually moving at some slightly less negative velocity. So I think this is a false statement. So B is false, so this can't be true. I think this is true. Maybe this is not true, and this is not true. Well, I guess I like A and I like C, therefore my answer would be F. A and C are both true. I think you want to think about that. That is tricky. That is extremely tricky. You and your work group, I think, are going to spend a while puzzling through that. So that was kind of a hint. You're going to see a problem that asks you how tall is the building based on this premise, and you're really going to have to puzzle it through a little bit with your teammates. So I will see you on Monday, and we will do a worksheet on acceleration, Mazur's chapter 3, worksheet number 3.